Hello. Today's lecture is on the rate and regioselectivity in electrophilic aromatic substitution. So you'll have to go back to last semester to think about what regioselectivity means. It's literally meaning the idea that that whatever we're substituting is specific or gets specifically placed in one location over another location. Okay, so let's see what we're talking about. So we have two organic aromatic compounds that, for all intents and purposes, are approximately the same size. We have toluene, then we have trifluorotoluene. So the only difference here is the fact that in the trifluorotoluene, the three hydrogens have been replaced by fluorine. Now, on both of these, we're going to do a nitration reaction. So if you remember from the last class, for nitration reactions, what were the conditions here? Well, for nitration, obviously we're going to be using nitric acid. And we do not add a lot of heat, because otherwise we'll use sulfonation. But the other reaction condition is that it required sulfuric acid. And you would expect that you would have very similar results, that you'd have the nitrosyl group ending up being placed on the benzene ring, and most likely in the same location. However, this is what happens instead. So what happens instead is, on the toluene, they get two major products. Okay, they get it in the ortho position. So remember, the position next door to the group is called the ortho, or the O position. And that happens approximately, that was 63% of the product. So 63% was ortho. And about 34%, so you get another major product, 34% was para position. Whereas if you look at the trifluoromethylbenzene, so the only difference, once again, is the fact that the three hydrogens have been replaced by fluorine, you only get one major product, and it's in a meta position. I would never ask you to memorize these numbers. Not only did you only get one, but amazingly, that's not what I'm wanting. Let me see if I can find a good color, a different color here. Amazingly, the one for the meta position is, well, that's not a good color either. The one for the meta position is actually 40,000 times slower. So it's much, much slower than the one that is than the toluene, which directs it to go to the either the ortho or the para position. So first of all, we have to be able to explain the reasons why, and secondly, we also give these special names. And so what they do here is they call the one for toluene, they say that this is OP directing. So this is an OP directing, or an OP director. The one that was for the meta is in meta directing, or the M directing. Because the major product goes into the M position rather than the O or the P position. So how can we explain this? So now I've drawn a benzene ring that has just a non-hydrogen substituent. I'm going to call it R. Okay? So let's suppose if it's going to happen, if the substitution happens at the ortho position, then let's see like what the intermediate looks like. Because there has to be something different about if it's an ortho or a para position versus a meta position. So let's go ahead and draw our mechanism for what happens. So we have our EY. What happens whenever we're doing an ortho-substitution? So first of all, the double bond swings out, boom, and the Y leaves, boom. Sound effects optional. So let's just draw this intermediate. Once again, this is if it's ortho. So let's draw the intermediate. These two double bonds and weights drawn are unchanged. We still have the R group, and we have the E on there. And remember, there's still a hydrogen that's attached on the same carbon as the E. It's just not drawn in for clarity's sake right now. And we have a carbocation, which I'm going to put in a different color. Okay, so that way it stands out a little bit more. This is the carbocation. If this was a clock, the carbocation is actually in the meta position. If this was a clock, it would be like a 4 o'clock. Okay, so, but there is resonance that's possible. So let's just draw the possible resonance structures. One is that double bond can swing over. So what would that look like? So for that resonance structure, we still have the R. We have our benzene ring, or what had been the benzene ring. There's the E. Now the double bond's here and here. And so where is the carbocation? It's also in the meta position. So even though this was an ortho substitution, the carbocation is in the two meta positions, but we still have another possible resonance structure. This double bond here at the top can actually come down and swing down like that. Boom. Sound effects optional. And we have another possible resonance structure. So let's draw what we have. So now that new double bond is there. There's the old one. The R is still attached in the same position as is the E. Okay. The new carbocation, which I'm going to put back in that other color, is here. It is at the carbon. It's located on the carbon that the R is located on. So once again, these are the three possible resonance structures. I'm going to put a big bracket around them. So this is what happens whenever we have the ortho position. So why does that matter? Well, why that matters is if your R group, let me use a different color on the highlighter. If your R group here is something that can loan electron density or has lone pair electrons that can go down and help out, it can actually help further stabilize this carbocation. So if you think back to last semester, remember when we talked about induction and hyperconjugation? So groups like CH3 or any alkyl group, it could be not just a methyl, but an ethyl group or propyl group, anything like that. The electron density from that carbon, from this carbon here, can actually be spilled over or donated to help fill out that carbocation. That's the reason why a tertiary carbocation is more stable than a secondary, which is more stable than a primary. The more friends it has to help out, the more stable it is. So toluene, where the R group is the methyl group, it has electron density that can donate or help loan. It's electron donating. Whereas, let me erase this. When that R group, whenever the R group looks like, here, let me just use a different color. Look like this, which I'm going to draw all the way out. Whenever it was CF3, So here's where the benzene ring would be attached. I don't have enough room to draw all of it. But see, there's the carbocation. Now, the problem is this carbon does not have electron density to help donate to that carbocation. It's electron deficient. The reason why it's electron deficient is because we have these three fluorines that are so electronegative that they're pulling all of the electron density towards that side, towards the other side. So it actually destabilizes that carbocation. Okay, so now let's just draw, let's look at what happens, or maybe on your own, if you want to pause the video, is draw what it looks like, the reaction and the intermediate looks like if it's meta-directing. So you may want to pause it and work out the mechanism and what the intermediate looks like if it's a meta-director. Let me switch back to the lighter color. So if it was meta-directing, these are R, E, Y. Now we're going to have boom. It's going to swing out and take the E. Once again, the Y gets kicked off. Sound effects optional. I'm going to go ahead this time and put the brackets because we already know that there's going to be resonance structures possible. But let's draw what it looks like. You draw your benzene ring, or what had been the benzene ring, and this is where the E is located at. That double bond is intact. This double bond is intact. Now, where is the carbocation? Now the carbocation is in the ortho position. Okay, which that's fine. There's nothing wrong with that. So now we have another resonance structure that's possible. So you swing that over. Let's draw what it looks like now. So now the double bond is there and there. The E group is still hanging off. Remember, there's still a hydrogen that's attached to that carbon. And the carbocation is in this ortho position. Okay, but we're still not finished. There's still another resonance structure that's possible. Boom. So I'm going to draw it down below because I'm running out of room. So we have the R group, the E group, the double bond is now here, and the carbocation is located in what position? That's right, it's located down at the para position. Okay, and then I'm going to go ahead and put my end bracket. So if you notice now, the carbocation is never located on the carbon that the R group is located on. So this is the reason why whenever our R group, let me choose a different color. So now, whenever that R group looks something like this, that was very electron withdrawing instead of electron donating, you don't have to worry. We're never forming the carbocation here. It never happens. Instead, the carbocations are going to be one removed. It's still either here or there, or it's going to be all the way to the para position. Now, please note, it's still not activating. That's one of the reasons why it's still slow. It's still slow because electron density is still being pulled in this general direction. So it's going to destabilize that carbocation, whereas something like a methyl group actually stabilizes it. On your own, you can work out the mechanism of whenever the electrophile is added in the para position, and if you do, or when you do, you're going to find out that the carbocations form in the same locations as they do in the ortho position. Okay, so there are some. This just goes to explain the reason why we have certain substituents. So what happens when the R group oops here. So what happens when R equals, and then, for example, we already know that when R was equaling a methyl group, it's called an OP director. When R was equal to CF3, it was M, and it was slow. Okay? Well, if R equals NH3, or NH2, I'm sorry, the question is it going to be OP or is it M? So let's just draw what that R group looks like. If you draw it out with the the Lewis structure, it's going to look like this. It's going to have 2 lone pair electrons. So therefore, whenever the carbocation is right there, these 2 lone pair electrons can actually go and help stabilize that. And you get another resonance structure out of it. So because of that, an NH2 group is also an OP director. Let me try to erase this so that way I can write it on there. Okay, so NH2 is an OP director. OH is an OP director because the oxygen itself also it's directly attached, and it has lone pair electrons. What if the R group is something like this? Is an aldehyde. Well, now if we look, the atom that's directly attached to the benzene ring is a carbon. If it was an alkyl group, we would say that it could help, something like a methyl, ethyl, propyl. It could, or even an alkene type of group, it could add electron density to it. However, it's not. It's a carbonyl group, an acyl group. And this oxygen here is 1 atom removed. And so it's already pulling the electron density towards the oxygen. So it makes that carbon electron deficient. And so this one is actually going to be an M. So I'll do another video tutorial where we just talk about the rate, like how fast some of these go, and we'll also do more examples of whether it's an M director or an OP director. Hopefully this is at least a good initial start to this conversation, and I'll see you in class.